Yes.
I think the transition region determines pretty much the signal-to-noise ratio at which the values are going to map correctly from 0 to 1 and vice versa.
Okay. So actually, there was a point by Berkeley, somebody in the yellow.
Saying that they need they'd specify like a range, like the 0 they have a range, the 1 have a range, and they wouldn't actually touch. There would be a midland where it's not a valid input.
So in fact, you can argue that the device doesn't have to actually guarantee anything to you in this transition region or this forbidden zone. Okay? So a contract would be as long as you're playing by the rules, as long as the signal you give to this device is within the range that is specified by the device, it's going to give you the right behavior. Right? So as long as the range of input that you give it is here, it's going to give you a better representation of 1. As long as you give it the right input here, it's going to give you a better representation of 0. And that's actually all that it needs to provide. Okay? So as long as you're giving it good kind of digital signals, it's always going to give you good digital output. Right? And what it does in the transition, in principle, doesn't really matter to this contract. Right? And if you ever give it an input that's somewhere in the middle, no guarantee. So you basically broke the contract. The device no longer has to guarantee anything to you. Okay? Now, why would you want then a fast transition between these two regions? Yeah?
If you wire up 2 of them,
Yeah.
you do a fast transition, it will avoid that out-of-contract region in the middle.
Yeah.
As best it can.
So exactly. So when you have fast transition between those two regions, that allows you to spend essentially less time in there, but also it has better noise properties, right? So the device is actually able to handle larger fluctuations in the input and still perform a good digital function, right? So if you had something where, for example, only you had a very small region and then kind of gradual change over here, then your noise margins would be very small, okay? So this would be 0, this would be 1, and some small perturbations in the system may drive you into the kind of the forbidden zone, and the device may no longer function properly. So in terms of better and better digital devices, a faster transition allows you to have more robust behavior. Okay. Now, what other behaviors might you want with this device? And I, again, want to emphasize that digital behavior is useful, but there might be other behaviors that we want to be able to implement. So if you didn't, let's say if you didn't want just digital behavior in the system, in terms of the transfer function, in terms of the input-output relationship.
So if you wanted an analog signal, if you had your sloped region more extended, you'd have a better dynamical range from which to get a degree of inputs and a degree of outputs.
Yeah, exactly. So you may want to have just some kind of graded response that allows you to take an input signal and convert it to some kind of a graded response where you might care about creating an enzyme that matches the level of some input in the system just right. So you may not want to have an enzyme that's either produced or not produced. You really want to have a graded response. Or you may want to have, so this is the digital behavior that we looked at, so inverse sigmoidal with a sharp transition, high gain would be useful for digital inversion. You might want to have something where, for example, you have amplification, right? So a situation where whenever the input is very low, you still have a high output, but as the input goes up, even small amounts, you have a very fast response that kind of overcompensates. Okay, so you might want to have an ultra-sensitive response with some kind of an amplifier function. You may want to have responses that are tuned to specific thresholds. So you might want to say, I want to have a response where it's only going to function when the input is above this low threshold and below this high threshold. Okay, so you may want to have high levels that just operate right here. When it's too low, too high, you may not want to have the response. Okay. The other thing you want to consider is what is the time behavior of this device. So as the inducer, let's say we have some kind of an inducer coming in, as the inducer rises, what is the timing of the response? What is the time going up? What's the time going down? So the notion of the steady state behavior is useful, but certainly as we develop these models for these regulatory systems, we want to always keep in mind what the timing behavior is. Okay?